So we had already obtained the stress strain plot, or rather the plastic strain versus the stress that is beyond the yield stress, that plot generated. And um, now, if you recall, this particular Excel sheet uh, had only the extensometer strain, and we have created also another Excel sheet where the entire strain data is there. Uh, so this is the tensile extension, and this is the load, and this is the radius. So the diameter was 6.38 millimeter. Therefore, the radius would be 3.19 millimeter for the specimen, and the gauge length is 25 millimeters, and therefore the cross section area turns out to be this much millimeter squared. And in order to get the strain, once again, what we have to do is we can divide the tensile extension with this particular gauge length. And to get the engineering stress, all we have to do is divide the load with the cross section area, the original cross section area. And after we have done that, we can copy these two columns or this particular row, so up to the end of the file. Okay, so if we do that, we will have the engineering stress strain plot, and if we take that and if we insert a scatter plot, this is how it looks like. Now, this is what we actually obtained in the PDF file as well. So if you look into this PDF file, this is exactly the same plot that is there. The one thing that is to note there is that once the extensometer is removed, suddenly the slope seems to change abruptly. The reason I use the word seems, because that is not exactly what is happening. Because once the extensometer is removed, once again let me repeat, the calculation of the strain is not accurate. It's actually the crosshead movement that is being fed to the additional extension. So it's not particularly scaled or anything. For example, if you plot time versus engineering strain, so this, remember, this engineering strain that we calculated is just the tensile extension divided by this gauge length. So if you take this time and if you take this engineering strain and make a plot, you'll see that at one point there is a sudden change in the slope. Okay, so the moment the extensometer is removed, there is a sudden change in the elongation, and that is because beyond after removal of the extension, the crosshead movement is being used in place of the actual extension over the gauge length. And since that is happening over a larger length, so that is actually typically larger than the what it is happening uh, inside the region where the extensometer was placed. So what the first thing that we are going to do here is we are going to make a copy of this plot, and let me paste it here. Okay, so for one plot we'll have the first segment, and for the other plot we'll only have the second segment. Okay, so for example, therefore we'll have to we'll have to select data, and we'll have to edit, and instead of taking, let's say, up to 1,61,000 data points, we'll only take up to 30,000. Also remember, within the elastic limit, the strain actually occurs much slower, because the entire setup of the UTM also undergoes elastic deformation. So because of that, we'll also remove first few rows, let's say first 1,000 rows, or let's say first 3,000 rows of the data. So once again we'll do the same with the extension as well. So this is the earlier row was simply of that of the time, and this is for the engineering strain we are doing. Over here also we'll take up to 30,000. Okay, and if you look at it, even here a portion of the elastic effect where the strain was happening quite slowly, that is visible. So what we can do is we can change from 3000 to, let's say, 5000. Okay, now we'll change the chart type from line plot. Let's make it just a point scatter plot, and in that what we will do is we will fit a straight line. We'll just fit a straight line, and we'll show the equation, and of course the r square value is 1. So if you can see, this is what is the actual strain rate, which is 9 into 10 to the power minus 5. If you recall, we are approximately using a strain rate of 10 to the power minus 4 per second. So this is the actual strain rate, 9e minus 5. It lacks precision, but that is still okay for us. Okay, so we'll take this value, just the aim value. So if y equals mx plus c, we are only taking the aim over here, and the same thing we'll do over here as well, but over here we'll select the data up to the failure, but the starting data should be, let's say, 40,000. Starting row should the starting row should be 40,000. Okay, and once again we'll change the chart type to scatter plot, add a trend line, and we'll notice that the slope here is actually higher. So here it is saying the strain rate is actually more than twice. So we need to find a correction factor for our engineering strain that is over and above 15%. If you recall, the 15% of engineering strain was the strain where the extensometer was removed, and that scaling factor would be simply this divided by this. Okay, so this factor we will multiply with any additional strain that is happening to the specimen beyond 15%. If you put these set of plots to the left, so we'll now try to modify the engineering strain. So this is what we are going to do. So we'll use if-else criteria. So if the engineering strain value is less than 0.15, we would output the same value. Otherwise, what we will do is anything that is over and above. So just look at this formula. So we are keeping 0.15, but anything that is above 0.15, that is G3 minus 0.15, okay, will multiply with this scaling factor. Okay, and let us just copy this one till the end of the file. Okay, now let's look at this particular plot. In this plot, currently we are using the x-axis to be this particular strain. Instead, if we just take this particular row Let's see what happens. So we'll replace G's with L's. So suddenly you would notice that this plot is kind of being cured. So it no longer looks like that the slope has abruptly changed. It's of course there is a dip because there has been a small unloading at the time of removal of the extensometer. But apart from that, okay, this curve is plenty smooth, and the slope is also changing continuously. It's not an abrupt change in the slope. One more thing I need you to notice that that about 50% of the strain, about 50% of the strain, some serrations are happening. This seems to be either type D or type A type of serrations. Let me tell you, 304 stainless steel 304, the material that we are testing here, it is a material which shows dynamic strain aging, and particularly at low strain rates such as this one, that is 10 to the power minus 4. And since we are doing the experiment at room temperature, it is highly expected that the effect of this is known as PLC effect. This PLC effect, or Portvin-Le Chatelier effect, that is typically visible at higher strain. So so you see this at higher strain, you are observing this behavior. Okay. Uh, okay. Now what we will do now is we'll leave this plot over here, and let's look at what we already had from the previous video. So there we had the stress versus true strain plot. So in this case, the y-axis is stress, that is over and above the yield stress, and the strain that is there in the x-axis, uh, that is the true plastic strain. So this is true stress versus true strain plot, but the stress is over and above the yield stress, and the strain is plastic strain. Okay, and we can copy this data from over here. That's exactly what we have done, and we can store it in a text file. Okay, but if I store it in a text file, recall how many rows are there. That is nearly 34,000 rows that are there. That many rows or that many set of data points is seldom necessary for fitting a material model, and we would particularly fit a Chaboche material model. And before doing that, I would like to say a few things about the Chaboche model. And this is the same word file that we have seen in the previous video. We have only seen these particular equations. This Chaboche model is a hardening model. Now if the material didn't have any kind of hardening, then the stress strain diagram would be elastic, perfectly plastic, which means beyond the yield point the stress strain diagram would be horizontal. Okay, which means beyond this point, the yielding point, this curve would be straight, flat. That is there would be no slope. The slope becomes zero. But since such is not the case, we can expect there is a hardening. And now Chaboche model is classified as a kinematic hardening model. There are two types of hardening in plasticity: isotropic hardening and kinematic hardening. What are they? You can learn about them from a theory of plasticity book. I can suggest the one by J. Chakraborty. Mm, uh, so from there you can learn about isotropic and kinematic hardening. You may also look into the books by M.A. Crisfield. M.A. Crisfield, I think the title of the book is Nonlinear FEM. So there are two volumes. You can also look into those set of books to learn more about different types of isotropic and kinematic hardening model. However, since we only have a tensile test data, we didn't do any kind of cyclic test, we cannot know for sure the hardening in the material, that is 304, is due to either an isotropic isotropic hardening or due to a kinematic hardening. but then again we have a choice to go with either one, and here I'm going with kinematic hardening. Okay, Chaboche kinematic hardening model has multiple Chaboche terms. Okay, and all of them together contribute to the hardening of the material. So the stress that is over and above the yield point is a sum of different hardening stresses, and they are actually called back stresses, or let's say the sum of the all of those xi's are called back stresses. But these individual xi's are the individual Chaboche terms, and they have their individual set of parameters. For example, if the material model has three Chaboche terms, so there would be three pairs of Ci's and gamma i's. These are the material parameters. Apart from the yield stress, which is also a material parameter, these Ci's and gamma i's are material parameters. Okay, and yes, the Chaboche material model gives you a behavior which looks like this, which is different from a linear behavior. It's not a linear behavior. It is kind of gradually the slope is dying down. So that sort of behavior can be modeled using a Chaboche model. So this is a uniaxial form of the model. Of course, this particular material model is a 3D material model. It's a kinematic hardening model. So of course, it's a 3D material model, which means all the 6 components of the stresses can be defined through this. Also, if you notice, this particular material model is only defined through differential, but this is only I have done for a better representation, but this is actually typically represented in terms of the rate. So this dxi would be divided with dt, and you'll have xi dot, and that would be a function of epsilon p dot, that is the rate of change of plastic strain. So this xi is individual Chaboche terms. Their rate of change depend on the rate of change of the plastic strain. Although it is a rate independent plasticity model, and being a rate independent plasticity model, you can simply drop the dt from either side, and it simply becomes a function of the plastic strain increment. You might notice that the two d epsilon p's that are there, one of them is a signed quantity, the other one is the absolute value or the unsigned quantity, even when you are looking at the uniaxial model. So depending on you have a tensile or a compressive loading, the signs would matter for the first term. For the second term, it would not. And from the uniaxial model, we have also constructed the tensile form, uniaxial tensile form, wherein the two d epsilon p's have the same sign. So of course this one is positive, and also because the loading is tensile in nature, so this d epsilon p is also positive. When you do that, so you can the uniaxial form becomes this one, which can be very easily integrated to have this type of exponential form of the Chaboche term, individual Chaboche term. One more thing to notice, that if you set gamma I equals 0 for one of the Chaboche terms, which we typically do if there are more Chaboche terms than one. If there are multiple Chaboche terms, we would set for one of them gamma I value, we would set it to be 0. And what does that mean? In this case, of course, this becomes a singularity. You cannot divide something by 0. But then it becomes a 0 by 0 form once you expand this exponential form. Because you see, this is, you will have the two ones cancel out. And then you have order gamma I squared terms, and this term that is linear in gamma I, that just gets divided by gamma I, and eventually the gamma I doesn't matter any longer. So when it tends to 0, you have a linear kinematic hardening model. So the material hardening model for the individual xi, individual Chaboche term, becomes linear. Okay, that means the individual Chaboche terms changes linearly with the plastic strain. So, for example, if you look at this particular plot of the stress versus plastic strain, after some initial settlement, this curve is more or less linear. Okay, and we have actually done the calculation, and we figured out this particular slope is around 2 GPa or 2000 megapascal. Okay, so this portion that is linear, so there is some initial settling that is happening. Okay, so initial part there is the slope is gradually dying down and ultimately becoming zero, but then for one particular Chaboche term, so we are guessing there are more than one Chaboche term, and we are it is a good guess to take between 2 to 3 Chaboche terms, and to be on the safer side we are taking 3 Chaboche terms here. And let's say for the third Chaboche term, the slope is constant, and basically it's a linear term, and for that linear term it seems to be having a slope of 2 gp or 2000 megapascal. So we have a rough estimation of that. Okay, for example, it is changing from 300 to 500 in a span of let's say 10% strain, so 0.04 to 0.14. Remember, this is true plastic strain, so it is much lesser compared to 0.15 from where we remove the extensometer. So since 200 megapascal is changing over zero point 0.1 strain, that is 10% strain, so the slope over here is around 2000 megapascal. So that's what is we are estimating. Okay, so we'll keep that estimation in mind. So one of the Chaboche term will have Ci value of 2000 and gamma I value equals 0. So remember that. And next thing what we did, so we had this true plastic strain versus true stress beyond the yield stress data stored in this file, which we are calling sigma versus epsilon. And remember, this has 34,000 data points nearly, so we don't need as many. So next thing that we are doing is we are logging into MATLAB online. If you do not have a MATLAB license, that is the best thing to use, and that MATLAB actually lets you use 20 free hours of usage over a month, every month, and that is more than sufficient for us. What I have done is I have saved that text file, uploaded that text file in my MATLAB drive. You will find enormous videos regarding how to create an online account and how to save files in the MATLAB drive, or how to use MATLAB online. So I'm not going into that detail. What I'm doing here is I'm showing you how I have created a folder in my MATLAB drive named tensile parameters or tensile param, and there I have saved the text file with the data. And I have also created a MATLAB script file, or a MATLAB function file actually I have created. I'm calling it shab for Chaboche fit .m, and I have actually opened that file here. Okay, let me close this window, let me reopen it. Okay, so this particular file I have created, so it is a function in itself. Okay, so you can either mention the number of Chaboche terms that you want to fit, let's say 2, 3, 5, 10, whatever, or if you do not put any argument, if you simply run this function, so this function can run without any input argument. If you do that, then it automatically assumes that you are going for 3 Chaboche terms. Okay, that's exactly what we are also going to do. We are going to run it without any input. So this is a function without any input argument, and it would automatically think that it can use 3 terms. Now, I'm not going to share any link for this program or anything. You can, however, freeze the screen or take a screenshot and write the program down on your own. But I'll be gradually explaining all the things that I'm doing. So the first thing that I'm doing is I'm just reading that particular data file and that many rows and storing it in a matrix which has a size of this many rows versus this many columns. Okay, essentially it has one particular column for the strain data, the another particular column for the stress data, exactly like this text file. Okay, and after that what I'm doing is I'm just filtering some data out. So I'm only taking every 1 in 300 data. and this is the syntax for that. So at the end I'll have nearly 110 data points, and that much is sufficient to fit, 3 Chaboche terms. Okay, actually even lesser would be sufficient, but we are going with 110 data points. So going from 34,000 to 110 data points. Now uh, now what I would be using is an optimization. So essentially what we are trying to minimize is this another function which I have named as what is that function? Yes, this function, which one I'm calling as the squared sum error. So we would be trying to minimize the squared sum error, and I have defined that function as well. So I'll go wherein I'll assume some Chaboche parameters, and try to reconstruct for those 110 data points the stress values corresponding to those strain values, and check how much is the error between the actual stress values that are the ones we have obtained from the experiment and the ones that we have obtained from the Chaboche parameters. And in a way there is a routine. I have used fmeancon over here. Initially I wanted to use a genetic algorithm, but apparently with no with free license, MATLAB Online only lets you use fmeancon, and the optimization toolbox is not available, so you cannot use the genetic algorithm. So this is what I am doing here. Okay, so so first I have read that data, and I need to have uh, the minimum values of the Chaboche parameter and the maximum values of the Chaboche parameter, and I'm initiating that vector of minimum values with 1500 versus 0. So this is like the Ci parameter, and this is like the gamma I parameter. I'm initiating so these are the let's say this is for the first Chaboche term, and the maximum values for the first Chaboche terms are 2500 and 0. So as we have observed that the linear part of the stress strain diagram, that has a slope of 2000 megapascal. So we are keeping that within the range of 1500 versus 2500, and gamma parameter for that Chaboche term we are keeping it to be 0. The minimum value is 0, the maximum value is 0. And for the rest of the terms, that is from 2 to n, okay, n being the number of Chaboche terms, we are setting a limit for the Ci value from 0 to 10 to the power 6, that is 10 to the power 6 megapascal, that is 10 to the power 3 gigapascal, and similarly the gamma I value goes from 0 to 10,000. So we have done some trial and error. I figured out that this actually works best, uh, and uh, and the routine for squared sum error, that doubles as a fitment plot. Okay, when the plot flag is false, it does the it calculates the squared sum error. When this flag is set to true, and that is how the program has been written. Mm, so if it is set to true, then after the fitment is done, it takes the parameters and does a fitment plot for the checking of how good the fitment is. And this is the fmeancon command. It requires the function which would be used for the fitment operation, mm, and then it requires an initial guess and a set of conditions, linear constraints. Some are equality constraints, some are inequality constraints. We are avoiding that. The only constraint that we are putting are the minimum values and the maximum values, and some options I have put in order to set the tolerance value, the maximum function evaluations, and also whether to use parallel computation. Of course, with MATLAB Online, this parallel computation would not work, particularly with a free license. And also I have used some plot functions. So every iteration, the minimum value of the function would be plotted, and gradually wherever that converges, that value would be plotted. So a continuous plot would be shown over here. Okay, and that's why this particular function ends. By the way, after the fitment is done, I am running the SSC routine, that is the routine for the squared sum error once again. This time the P flag being set to true, which means this time it is not giving you the squared sum error. Instead, what it is doing is, it is just plotting the fitted curve versus the experimental curve. Okay. And I'm set next I'm using going into the details of the SSE routine. So what it does is it creates another matrix B, which is essentially a single column, which will have the fitted value. So A has the strain versus stress experimental data, and from that, actually, if the yi value is 0, so yes, so from all the Chaboche parameters, we are identifying the ci parameters and the gamma I parameters. If a particular gamma I value is 0, so linear calculations are being done. If a particular gamma I value is non-zero, then this exponential term is included. This is for the simplicity of the calculation, and also avoids error, zero error, wherever the Effincon kind of diverges. So that sort of error can be removed by using this technique. And the rest of this portion is only for plotting. So when the PF flag is true, that means we are no longer calculating the squared sum error. This particular portion would be used to not only create the plot and not only create the axis and the legend, but also save it as a plot fit result image. So I'm saving it as a PNG file. On the other hand, if the PF flag is false, then we are calculating the squared sum error, which is basically the dot product of B, the fitted stress values versus the experimental stress values with itself. So basically the squared sum error. Okay, so we can what you can do is you can go back and take the screenshots and you can write the program on your own. I'm not just handing you over the program. But now this is a time to run this program, and once I run this program, a figure window will open, and it will show you the Effincon routine going through a convergence. You might have to run the Effincon routine multiple times to have the best convergence, because Effincon uses a random initial value. Depending on the initial value, the convergence the quality of the convergence can also vary, because Effincon, being a gradient based method, can only give you a local minima. If instead we could use a genetic algorithm, that would give us a global minima, but that also takes a lot of time, and also MATLAB Online doesn't allow you. So I'm running the Effincon routine over here. I cannot see the figure window just opened. Yes, so it is converging from 10 to the power minus 7 to, I don't know how small. I think, if I enlarge this, the final value would be shown. So it started from something the order of 10 to the power 7, okay, and it finally converts to something like 800. Okay, so it converts to 800. Okay, and you can see the fitment value. So this red dots are essentially the experimental data points, and this blue chain line is essentially the 3-term Chaboche fit, as the legend says, and it actually is quite good fit. I mean, they are barely distinguishable. As far as the material feed goes, they are barely distinguishable. Also, the program automatically prints down all the parameter values. So if you look at the first parameter, that is of the order of 2000, the CI parameter is 2000 and the gamma is 0, and the rest of the parameters are over here. But this is a fit that I have obtained. Do not try to copy this, and you can do a fit of your own. Okay. And if you're worried about the file, so I can show you the file. So if you go back to MATLAB Drive and double click on the fit result, you can actually open this file, and you can actually download also. You can also download this file, and if you want to attach it to your report, you can also do that. Okay, you can attach this thing to your report the way, and it shows how you would have done the Chaboche parameter fit. Okay. So what I've done next is I have copied those parameters and gone to engineering data. And earlier we had done this material parameter for some other material, but this time we have renamed it SS304, and the Young's modulus parameter that we had obtained Okay, what we can do is, so we obtained the Young's modulus parameter over here. Okay, so that was around 190 GPa, so 189980. So we can put it over here, 189980. So that many MPa, right? So what we can do is, we can go back three places and put a decimal point, and this much GPa. These are the isotropic elastic parameters, and for the Chaboche terms, whatever we have obtained through the fit, we have put over here. We have simply copied them and we have put over here. So these are the parameters I have used, and I have also used the yield stress that I have obtained from the uh, mm, from the fit, or before doing the fit, what we have obtained by eliminating the elastic strain. So we have done that exercise in the previous video. To that thing, we have put over here. Okay, now the engineering data is complete. What we will do next is save the file, and then we'll open the model. Okay, it says the upstream data has been modified, so it needs to read it. Okay, it's still opening the mechanical window. Okay. So I've done some trial and error, and I have tried to make the mesh the same method, but I have tried to make the mesh more uniform, and tried to make them more unskewed, so more regular. Earlier the elements were even more skewed. Uh, so so now if you look at them, they mostly look like bricks. So that is the best way to have an best way to have you know this type of mesh. Now what else I have done is I have tried to use even finer mesh at the middle segment, okay, where the necking is supposed to happen, okay. And compared to the previous material model, I have done some more modifications. I had to, because this particular material has a very large ductility, which means the ultimate stress occurs much later. So this is what I have done is, first of all, in the analysis setting, acha, first of all, the displacement, that is a, if I show all the bodies, so the maximum elongation I have changed to 60 millimeters. That means, or maybe even you can do is what you can do is 50 millimeters. That is, remember, this portion from this line to this line over here, this circular segment over here, that is around 30 millimeters. So this uniform portion is about 30 millimeters. So I have applied an elongation 2 times, or nearly 2 times that length. Okay, so I'm expecting more than 100% of strain. Okay, firstly. Secondly, because of that, I have also, since the yield stress value now is really small, so if you look at SS 304, the yield stress value is 64 megapascal. So what I have done is uh, I have used the initial number of substeps and maximum number of substeps to be 30,000. Okay, so that otherwise I was facing a divergence issue. And next, nothing else has been changed. The large deflection is still on, and weak spring is still off. And what we can do next is we can now start the simulation. Okay. So initial set of time increment would be of the order of 10 to the power minus 5. So it is 3 times 10 to the power minus 5, and gradually it will increase. So once the convergence starts occurring, so already the convergence started happening. So because it is already within the elastic limit, and time step is really small, so the convergence is occurring very easily, and time increment is happening. Now it is of the order of 10 to the power minus 4, and the minimum number of time step also has been changed, that is changed 200. So it will take more than 200 time steps, so around 250 time steps would be required for the convergence. And it is already close to 10 to the power I mean 5 times 10 to the power minus 4. If you look at force convergence now, uh, it is not diverging, but the norm, the force norm, is already going above the tolerance. It is because at this particular only this much. Okay. So in nonlinear FEM, the residual or the norm of the residual actually needs to be checked against a tolerance. Uh, of course multiplied to a reference value and all. If you have used ANSYS, you would know that. Uh, within the elastic limit, that actually automatically happens. But when the yielding starts happening, then the solver has to check between two different slopes, and because of that, the residual. So no bisection is happening right now. But if you take much larger initial time step size, or much smaller number of substeps, initial number of substeps, then that can actually also happen, that the bisection may happen or even divergence may happen. So it is always good to be on the safer side by taking larger number of initial number of substeps, larger initial number of substeps, so that even when the yielding is happening, which typically happens at the very beginning of the uh, mm, plastic deformation, so or very beginning of the solution, so you can expect the time step is still smaller. So no bisection is happening, and the that means the time step is not decreasing, and the norm is only going outside of the tolerance for a little bit. Okay, and not a lot of time steps or sorry, iterations are required for the convergence. uh, Once again, the maximum, sorry, the minimum number of time steps that you have taken is 200, and it might seem like that is a overkill, because the convergence is happening practically at each iteration. So iteration number and the number of substeps are essentially the same. But if you pay a little attention, you'd realize that the specimen is about to elongate more than 100%, which means each of these substeps are resolving more than 0.5% of strain. Okay, that is 5 into 10 to the power minus 3 strain. That is quite huge, even for plastic strain. So we are mostly on par with the with the necessary number of substeps. So it is not an overkill, and particularly when you encounter the ultimate point and all, in order for accurate modeling, that is also required. Uh, mm, Also, the purpose of having larger number of substep is not only having convergence per iteration, that is substep per iteration, but also it has something to do with accuracy, because we are resolving 0.5% of more than 0.5% of strain every substep. So we need that many substeps. Okay. Taking any less number of substep would give us probably inaccurate results. Okay. Now, now remember, at the beginning of this video, I mentioned that the Chaboche plasticity model is a rate independent plasticity model. Keep that in mind. This is not rate dependent. Okay, but the material that we are using has dynamic strain aging, which is manifested typically at the smaller strain rates. So it has a rate dependent behavior. Okay, so our challenge is to see that can we model the material behavior exactly with this rate independent plasticity model. Okay. uh, so I'll let this convergence happen. It will take probably a while. If we look at the convergence curve, so this one is the displacement convergence curve, but if we also look at the force convergence curve, that is also very similar. We would distinctly notice that there are two regions where uh, the the norm of the residual force goes outside of the tolerance value, goes above the tolerance value, and these two distinct regions are one where the slope changes rapidly. Okay, so the first one of course is happening at the time of yielding, where the slope goes from elastic to plastic, and the second one is happening where the slope is practically has become zero, or even negative. So force deflection slope has become negative over here. This is where the ultimate point, actually the ultimate point might have happened already a little bit before this. Okay, so right now I'm anticipating that this will actually stop with the divergence. So let's just see what happens. So it is already showing the so showing a nature where the bisection is due, because there are multiple iterations happening without the green lines, essentially convergence. So the loading is displacement control. Uh, so I believe the issue is not with displacement convergence. The major issue is with the force convergence, because now with displacement, essentially the stiffness has become negative right now. So let us see the time increment. Initially the time increment was small, and that exponentially increased over the converged substep, and finally it became fixed at 5 into 10 to the power minus 3. That is exactly what is 1 divided by 200. And the time also initially changed very slowly. Then it was changing linearly when the convergence was happening every iteration. That means one substep was converging at every iteration. Now that it is taking multiple iterations to converge each substep, again the time change has become really slow. uh, uh, I think for the most parts the simulation is over. I mean, it either ends with a divergence, or you might have to stop the solution. I think in a little while it will break into bisections. That is, red lines would be shown here, and finally the solution will diverge. But at this stage it has already converged up to 93% of the load. That means about 47 millimeters of elongation has already happened. Okay, so the force convergence went into a loop. So it was having a loop of bisection, repetitive bisections, and then convergence, and then once again bisection. And if we look at the time increment, it was going through a loop of where it was rapidly decreasing, and then recovering, and then again decreasing, and this will continue for a while. And the solution nearly converged up to 97%, and that's where the solution was interrupted. And with the with the partially converged solution, uh, you can see it has actually converged more than this, more than 55%. So we have so it has converged up to this point, 97%. So what we can do next is we can actually take the so we have output the directional deformation and also the force reaction. So where we applied we got the force reaction at the location or at the boundary where we applied the 50 millimeter elongation. So this displacement 3 what we have scoped here to get the force reaction, and the only non-zero force reaction should be the x component. The other two components are very small. If you look at the y and the z component, they are of the order of 10 to the power minus 8 minus 7, whereas the x component is of the order of 1,000 or something, 1,000, 10,000 something. Okay, so the first column, and if we, so it doesn't matter whether we take the x component or the total force reaction, that is the resultant, it is actually the same thing. So we are just copying this column over here, okay, and pasting it. So we no longer need this particular Excel sheet, this one where we have obtained this plastic strain versus stress data, true stress strain data for Chaboche fit. We are leaving as it is, and now we are moving into the other Excel file, which is the tensile data full, where we have the entire stress strain diagram. Of course, this is the engineering stress strain diagram. So we have copied the force reaction from the simulation and pasting it over here. Okay, and similarly, let us copy the directional deformations. Remember, we had scoped two nodes at two specific locations, that is, at the two ends of the 30 millimeter uniform diameter portion, the two extremes, we have scoped two nodes, okay, two vertices, to get the x displacement. Essentially they are showing, so this green one is actually close to the fixed side, and this red one is close to the side where, sorry, this blue one is closer to the fixed crosshead, and this one is closer to the moving crosshead, and that will give us the minimum and the maximum value of the elongation. And what we are going to do is we are going to copy these two columns, and we do not need the average one. The average one doesn't make any sense for us, so we are going to copy these two columns and paste them over here. Okay, so now what we are going to do is we are going to so of course this is an unconverged solution, so we are going to remove the last few rows of these results. So there are about 250, I believe, probably data points, because the converged number of steps are, you can see from here, 214 converged number of steps. The last one is of course not converged. This is a prediction, approximation, but this 213, up to 213, it is converged steps, because we have interrupted the solution. So we are going to take up to that many values, so we are going to just discard the last one, and for the rest of the values we are good to go. Okay, so this is what we are going to do. We are going to take the difference between these two. Okay, so we are subtracting this one from this one and dividing by the length of the uniform diameter portion, that is 30 millimeter. Okay, and this particular column, which is the force reaction. Okay, by the way, if we plot the force reaction, you will see something. Okay, so the maximum force value has gone close to 22 or 23 megapascal. Sorry, 22 or 23 kilonewton. Okay, so this is 20 kilonewton, and that is around 23 kilonewton is where the maximum force value has gone. Okay, experimentally what we had obtained was the force value corresponding to, so yes, again the load, the tensile strength was 23 kilonewton. Okay, of course the diameter was bigger, so there would be some deviation, but you see the load order is nearly the same. Okay, to calculate the stress, we are dividing this dividing this load with pi and the radius is squared. Remember, for the simulation we have used a diameter of 6, so the radius would be 3, and therefore square of that would be 9. So I'm dividing this with 9 pi, and we have the simulated engineering stress in megapascal. This is the simulated engineering strain, and this is the simulated engineering stress in megapascal. And now we are going to copy these two and paste up to that 213 rows. Okay. Now let us superimpose this simulated stress strain diagram with experimental one. Of course, both are engineering stress strain diagrams. So this is what we are going to do. We are going to add another data set where the x-axis is this column and the y-axis is this particular column. Okay, so you'd see that this in this portion, okay, in this portion they are barely distinguishable. So the earlier curve that we have shown is the so basically uh, this plot that we have seen, okay, this is different. This is actually obtained from MATLAB fit, and that too the y-axis was the stress beyond the yield stress, and x-axis was the true plastic strain, and this was the true stress, true plastic strain up to within the extensometer strain limit. Okay, whereas this particular data is has not the true stress or strain but engineering stress and strain, and also this exceeds much beyond the extensometer limit. So this is where the extensometer was removed. Okay, so slight unloading is there over here, and also the thing is the stress over here is the total stress inclusive of the yield stress, and the strain over here is the total strain, and both are engineering variants, not the true stress and strain. Okay, so the stress strain diagram that we have fit by taking the data within the limits of extensometer strain matches very well much further beyond the extensometer limit. Okay, so so it is valid near more than 40% of the strain. Okay, so we had taken the data up to 15%, and it is valid more than 40%. Let's say close to 50%, it is valid. Okay, but after that, the deviation happened, and of course, the ultimate stress values are different. Okay, so I need you to report the ultimate stress values. Okay, and also the strains corresponding to the ultimate stress value. Okay, however, the difference in the ultimate stress value is not that much. Okay, if you look at in this PDF file, you will see the ultimate stress value over here was 740 megapascal, but in this plot that is around I believe, yes, that is 829 megapascal. Now that is just 88 megapascal of difference. Okay, so that is not huge, at least not as huge as the plastic strain. Okay, so that has gone from zero point 0.6 to around 1.3. Okay, so so the total strain over here in the experimental data is zero point 0.6, whereas in the simulated diagram, simulated curve, it is 1.3. That is simply because the actual material is rate dependent, and beyond this point actually it starts showing, it has reached a strain value where it starts showing the serrated behavior. So it essentially shows type A serrations over here. Okay, so probably one can say that the initiation of dynamic strain aging is the reason for it to have early failure, that is to reach the ultimate stress point and have a fracture because of the because of having dynamic strain aging over here. That can be a possible reason, but you can see that the material curve that we have fit with only 15% of strain data, extensometer data, has been valid for much wider strain range, even beyond the extensometer limit. Okay, so so that is one positive side, but this failure may be attributed, this difference may be attributed to the initiation of dynamic strain aging, which is a highly rate dependent behavior.